Hey there, physics. So in our last target, we learned a little bit about kinetic energy and we learned a little bit about potential energy. Okay. And those two types of energy together are often referred to as mechanical energy. Okay. The potential energy, the energy stored in an object's height, and the kinetic energy, energy stored in its motion, together, added together, are called the mechanical energy. And today we're going to talk about kind of one of the foundational ideas in physics, what's called the conservation of energy. And we're just going to talk about mechanical energy. So today, the conservation of mechanical energy. So our target that we want to accomplish here is we want to be able to solve some problems related to the conservation of energy. Okay, so here's a basic idea. Okay, I have an object, and this is really just a squishy ball. It's got a smiley face on it. I have some object, and it is some height above the ground. Okay, when it's some height above the ground, it has some potential energy. Now, it's not moving, it doesn't have a velocity, so it doesn't have any kinetic energy. But what's going to happen if I were to, let's say, drop the ball? Okay, if I drop the ball, it's going to move in a downward direction, obviously, right? As it falls, its height will become less and less and less and less. What happens to its potential energy as its height becomes less and less? The potential energy goes down. But what happens to that energy? Where does it go? Okay, well, here's the idea. As the potential energy decreases, what's happening to its velocity? Its velocity is increasing. It's accelerating towards the ground. So its kinetic energy is increasing. So as the potential energy decreases, the kinetic energy increases, right? So that potential energy is becoming kinetic energy. Okay. When it reaches the ground, it's now at height 0. It no longer has potential energy. All of the potential energy has become kinetic energy, right? Same idea if I were to throw the ball up in the air. I just dropped the ball. Speaking of dropping the ball, if I were to throw the ball up in the air, okay, let's say it starts at a height of 0 where it has no potential energy. As it moves up, as it begins to move up, it's got a velocity, so it has kinetic energy. And as it moves up, it reaches its maximum height. At its maximum height, it's no longer moving, so now its kinetic energy is 0. Well, what's happened to that kinetic energy? Well, the ball's moved up. That kinetic energy has become potential energy, right? And so this is the big idea behind the conservation of energy. The energy never goes away. It can just be transferred between different types of energy, okay? And we're just talking about mechanical energy here. We're just talking about potential and kinetic energy. There are other types of energy where energy can go, right? It can become sound energy, it can become heat, it can become different kinds of energy. But here, we're just kind of limiting ourselves to the mechanical energy. So between potential energy and kinetic energy, the energy can transfer between them. All right, let's do a little math. So let's say we're talking about a ball or any kind of object that's either falling or it is being thrown up. Okay, so it's got some mechanical energy at the beginning of its fall, or it's moving up. At the beginning, it's got some mechanical energy. I'm going to call that ME1, mechanical energy 1. And then later, at the end of its falling or its rising or whatever, it's got some mechanical energy later. I'm going to call that ME2. And these two mechanical energies should be equal. Okay. So the mechanical energy at the beginning should equal the mechanical energy at the end. Okay, now the mechanical energy, we could break this into kinetic energy and potential energy. So the mechanical energy is the kinetic energy plus the potential energy. So mechanical energy at the beginning is the kinetic energy at the beginning plus the potential energy at the beginning. And the mechanical energy at the end is the kinetic energy at the end plus the potential energy at the end. Okay? Now, we have formulas for kinetic energy and potential energy. We have things that we can use to calculate those things. So let's put in some of those things, okay? Now let's keep in mind that as a object like a ball falls or is thrown up in the air, its mass doesn't change, but its height and its velocity does. Okay. So kinetic energy, if you recall, is 1/2 times mass times velocity squared, and potential energy is mass times g times height. Hopefully maybe you can see that there. Okay, now let's put these terms, let's substitute those in to this expression. Okay, so the kinetic energy at the beginning, I'm going to write 1/2 times the object's mass times its velocity at the beginning squared. And its potential energy at the beginning is its mass times g times its height at the beginning. Okay. Kinetic energy at the end is 1/2 times the mass times the velocity at the end squared. And its potential energy at the end is mass times g times the height at the end. Okay? Now you'll notice in every term I have the mass. So I'm just gonna cancel it away. I'm gonna divide it away. So I have 1/2 v1 squared plus g h1. And I have 1/2 v2 squared plus g h2. Okay. Now, if you like, what we can do just to make this like cleaned up a little bit, make it look a little bit nicer, I'm going to go through and multiply both sides by 2. I'm going to multiply everything by 2, so that this is just v1 squared plus 2 times g times h1 equals v2 squared plus 2 times g times h2. Okay. And now that equation here, we can use to solve some problems. Let's take a look at some. Okay, here's a problem. It says, starting from rest, a child zooms down a frictionless slide from an initial height of 3.00 meters. What is her speed at the bottom of the slide? Okay, well, some things we know here. We know that her height at the beginning, h1, is 3.00 meters. I also know her height at the bottom of the slide. She's reached the ground, the bottom, and at the bottom, her height is 0. So h2 will be 0. I also know g. I'm assuming that the child is not riding a slide on the planet Venus or something. So g is going to be, your negative 9.81 meters per second squared. And let's see, we know another thing, we know her speed, her velocity at the beginning, as she just begins moving down, is 0. So now I know these things. Let me go ahead and put them into the formula we just derived, and we'll solve and find what her velocity at the bottom is. What is her speed at the bottom? Okay, so v1 is 0. And I have 2 times negative 9.81 times 3.00. On the other side, I have v2, which is what we're looking for, plus 2 times negative 9.81 times 0. Okay. this right here is just 0. I'm going to grab my calculator and I'm going to work out what all that stuff is. And there I get, let's see, 3 significant figures. I get 58.9. Okay, sorry, negative 58.9. And then over here, we have v2 squared, and then that is 0. Okay. Now, you can see I'm trying to take the square root of a negative number here. Let's just kind of pretend that's a positive, make it a little bit easier. That's okay. So now we're going to take a square root of both sides. G is negative when it's convenient. When it's not convenient, we can pretend it's positive. Okay, we'll take the square root of 58.9. And I get 3 significant figures, 7.67. And being a velocity, I'm going to put meters per second on that. And there we go, fairly simple. Okay, that last example was an example of an object, kind of falling. This next example is an object moving in a more upward direction. So this one, it says, an Olympic runner leaps over a hurdle. If the runner's initial vertical speed is 2.2 meters per second, how high will the runner jump? Okay, so what it's telling me is the runner's initial speed, that would be v1, was 2.2 meters per second. Okay, I can assume that the runner started from a height of 0, so that h1 is 0. Then of course g, I don't think my runner is running on the moon, so let's make it 9.81 meters per second squared. Let's leave off the negative. Okay. On the other side here, the final velocity that the runner has, when they're at the very top of their jump, is going to be 0 because they stop moving up at that point. So this v2 is 0, and g is the same. And then the final height here, that's what they asked me to find. So let's put the numbers in here and let's work out what the answer is. Okay. So v1 is 2.2, that's squared, and then plus 2 times 9.81 times 0 equals v2, which is 0, plus 2 times 9.81 times h2. I'm just going to turn that into an h. Okay. Now, let's simplify a little bit. We got 2.2 squared. I'm going to grab my calculator here. 2.2 squared is 4.84. It's only 2 significant figures though, so I'm going to put 4.8. All that junk is 0. That's 0. And then 2 times 9.81 is 19.6. 3 significant figures times h. Oh, I'm sorry, that's not h squared. That's h2. h2. Okay. Now we'll divide both sides by 19.6. And the height, I got 4.8 divided by 19.6. It's 2 significant figures. So I'm going to round this off to 0.24. And being a height, I'm going to put that in meters. Okay. Now this number might be a little more convenient to look at in centimeters. 0.24 meters is 24 centimeters, which seems like an entirely reasonable height for somebody to jump. So maybe, I don't know about that far. Right? So there is an example of an object moving in a more upward direction. Fun fact, you could use the kinematic equations that we learned back in Unit 2, I think it was, to solve all of the same problems. but looking at the energy is sometimes just a little bit easier than looking at the kinematic equations. So we've looked at a couple examples. We've talked about mechanical energy and conservation of mechanical energy, and hopefully that helps us be able to solve some problems relating to the conservation of energy. So until next time, take it easy.